Hi everybody and welcome to session 18 of Field 2002, Logic, How to Defeat Your Foes with Reasoning. In the last session, session 17, I was looking at the semantics for general predicate logic. What we did was we introduced the core notion of an ordered entiple and used that to understand the extension of a relation with n many places following it inside general predicate logic. So for instance, if you've got a two-place relation, then what you're interested in are ordered pairs of objects or ordered tuples, and when you're putting forward the extension of that predicate, you're building a set of those kinds of pairs. When you're dealing with an ordered triple, you've got a set of, when you're dealing with a three-place relation, you've got a set of ordered triples. When you've got a four-place relation, you've got a set of ordered quadruples, and so on. And what we saw is that the way of understanding these sets, these extensions, is very much the difference between taking a list of objects versus taking some kind of ordered list, where you take that list and you impose a structuring over it. And for any given list of objects, there are lots of ways of structuring it, lots of ways of putting an ordering over it, and that is going to correspond to different ways of specifying the extensions of different relations. What we then had to look at was taking some of that understanding of these extensions for multiple place predicates and then extending that to understanding cases where you've got different orderings for quantifiers. So we had a look at cases where you've got the same two quantifiers outside the scope of a two-place predicate, where you've got different quantifiers and then the different kinds of structures, semantic structures that is, that correspond to making those different orderings true for a given model. What I'm going to do in this session is look briefly at complex quantified propositions. And a complex quantified proposition combines our semantics for our relations and our predicates inside general predicate logic with our semantics for the connectives in much the same way that we did when we were in monadic predicate logic to produce complex sentences that feature both quantifiers, multiple place predicates, and connectives like the conditional or the biconditional in order to say fairly complex statements. And I'll look at some basic cases of these, and then I will go through some examples of building or go through examples where we're evaluating sentences that are complex sentences that have quantifiers, multiple place predicates, and connectives in there against a particular model. And then in the last part of the lecture, I'm going to look at identity. I'll introduce you to the semantics for identity. Remember, one of the things I said when we were looking at the syntax for general predicate logic is that the real sort of differentiation for identity that happens inside logic, particularly inside general predicate logic, happens at the semantic level. So although we technically don't need to introduce a new syntactic item for identity because it's already there in the language, we do introduce this new syntactic item, this equality and the slashed equality sign. And we do that because semantically speaking, the identity predicate or the identity relation is treated quite differently to other predicates or relations that are inside the language. Okay, let's get started. Let's have a look at these complex quantified propositions. So remember, a complex quantified proposition is going to be a proposition that combines some of the features of monadic predicate logic some of the features of general predicate logic with some of the connectives from propositional logic in order to produce a complex statement. So here's a fairly complex statement. If there is an x and there is a y such that ax y, then for all x, for all y, ax y. So we've got two-place predicates in there, we've got quantifiers, we've got the connectives, and we're going to try and work out how to make sense of a statement like this. Or, so this is a sort of a case where the main operation is a connective, and the second kind of case we're going to look at is the case where the main operation is a quantifier. So this is a case where you've got some multiple place predicates in there, you've got connectives and you've got quantifiers, but the main thing you're trying to work out is a quantified statement versus the main thing you're trying to work out being a conditional or a conjunction or a biconditional statement. So we're going to look at two types of complex propositions, one where the main thing that's going on is something from propositional logic, and the other where the main thing going on is something from quantified logic, in particular the quantified general predicate logic. Okay, so let's take the first case. This is a case where we're combining some of our connectives from propositional logic with some of our complex things from monadic predicate logic, namely the quantifiers, with some of our relations from general predicate logic to come up with a complete sentence. So we've got something like this. And we want to try and work out how we determine whether or not this type of sentence is true or false. Here's the good news. The good news is that we deal with this in exactly the same way that we dealt with the conditional in propositional logic, in the same way that we dealt with the propositional in monadic predicate logic. Nothing has really changed. This conditional statement here, which is the main operation in this sentence, is the thing that determines the truth value, and this conditional statement has the same truth conditions as the conditional that we had in the propositional logic, which is to say there's only one situation under which this conditional is false, and that's when you've got the first thing but you don't have the second thing, and then all of the other situations that we could have for this conditional are going to make the conditional true. So I'm going to build a very basic model that makes this sentence true. I'm going to just have domain of two objects, and I'm going to set my extension for predicate A like this. So first of all, I'll make a case where it's true. And then we're going to look at a case where it's false. Okay, so in order to evaluate the sentence, we're really interested in, is the antecedent true, is the consequent true, because the thing we're looking at is the conditional. But in order to work out the antecedent here, we've got to work out something in general predicate logic, and similarly, in order to work out the consequent, we've got to work out something in general predicate logic there as well. So what are we doing here? Let's start with the antecedent, and let's work that out, and then we'll deal with the consequent. So the antecedent says there is some x and there is some y, such that A, x, y. Now, there are two ways to deal with these models. As we saw when we were dealing with monadic predicate logic, you can either eyeball the model and just work out by looking at the structure of the model whether or not the sentence is true. The more complex way is to take your quantifiers and look at all of the possible values or all of the combinations for those for the values that the quantifiers can take, for the values of the variables x and y, and then compute each situation in order to come up with an answer about whether or not the statement is true. I'm going to do it the hard way. If you can eyeball this, that's fine. You don't need to use the hard way if you can get the result out that way. But there are going to be sentences where you won't be able to eyeball it, and so it's useful to have the more complex way, the harder way up your sleeve as well. Okay, so we've just got two things in our domain. So we've got two values for x or y. So x can equal 1, or x can equal 2. Okay? And now from there, we've got two values for y. We've got y can equal 1, y can equal 2. And remember, for each value of x, we can set some value for y, so we're going to be interested in all the values for y for the values for x. And then we get this sort of branching structure that happens here. What we have to do is we have to try and work out, given the information in the model, for each value of x, whether this conditional is true. And we're trying to work out whether the conditional is true, so we're trying to work out whether the thing on the left is false or the thing on the right is true, because those are the two conditions under which this is true. So let's have a look at the thing on the left and let's see if it's true. So this says there is some x and there is some y such that A, x, y. So what we can do is we get A, and what we do is we take the value for x and the value for y, and we just put it in a little ordered pair next to A like this. And that's just a little sort of heuristic notation to just show us that what we're doing is we're checking to see if the ordered pair 1, 1 is inside the extension A. And what this statement is saying is that there's some value for x and some value for y such that A, x, y is true, which is to say there is some ordered pair inside the extension of A. Now we know that that's true because the extension for A is not empty, but what we're going to do is we're going to go through all of the options just to check. So we're going to check each of these ordered pairs, and we can build each of these ordered pairs out of all of the combinatorial options for x and y. And now we check to see if these are true. So, is 1, 1 inside the extension of A? Well, yes, because we've got that ordered pair there, so we know that this is true. Is 1, 2 inside the extension of A? Well, yes, we've got that ordered pair there, so we know this is true. Is 2, 1 inside the extension of A? Well, yes, we've got that ordered pair there, so we know that this is true. Is 2, 2 inside the extension of A? Well, yes, we've got that ordered pair, so we know that this is true. Okay, so what do we know from this? Well, we know immediately that there is some x and there is some y such that A, x, y. In fact, there are 4 cases where that checks out. We only needed 1, so we know the antecedent of this conditional is true. Now, given that the antecedent is true, we have to check the consequent. And so in order to check the consequent, what we've got to do is we've got to work out, is it the case for all x, for all y, A, x, y? Now remember what I said when checking these doubly universally quantified claims? In order for that kind of statement to be true, everything inside the domain, every combinatorial option that you can create from the domain, building an ordered pair out of those things that are in there, has to be inside the extension for A. Now, again, we can check that just by eyeballing it, and we can see that that is in fact true. I built this model to make this sentence true, so that's kind of unsurprising. But if we look at this structure here, we can also check to see that it's true the long way. So what this is going to say is that no matter what we put in for x, and no matter what we put in for y, AXY turns out to be true. So we can check each of the cases where we put something in for x and something in for y in order to see if it checks out for every such instance of A. So if we put 1 in for x and 1 in for y, then we get 1, 1 for this AXY claim, and we know that that's true because 1, 1 is inside the extension of A. When we put 1 in for x and 2 in for y, we get 1, 2, and we know that that's true because 1, 2 is inside the extension of A. When we get x equals 2 and y equals 1, we're saying that 2, 1 is inside the extension of A, and that's true. And finally, when x equals 2 and y equals 2, we're saying that 2, 2 is inside the extension of A, and we know that that's true. So we know that the consequent here is true. And then we just fall back on the truth table semantics for the conditional. When the antecedent is true, when you've got the first thing and you've got the second thing, then the conditional itself is true, making this complex quantified proposition true according to this basic model that I've built. Now, what would make this complex quantified proposition false? In order to make it false, all I need to do is just take one of these ordered pairs out of the extension of A. Because if I do that, then I know that I'm going to lose one of these options. Now what I took out just then was the ordered pair 1, 2. So here, where I set x equals 1 and y equals 2, it's no longer going to be the case that this is true. So this is going to be false. In order for the doubly universally quantified statement to be true, it has to check out for every value of x and every value of y, right? So every possible value of x and every possible value of y given some value for x. And because it doesn't check out for one case, then this sentence is going to be false, which makes the consequent of this conditional false, which means you've got the first thing, but you don't have the second thing. The other interesting thing I want to show you, though, is that suppose I do that, but then I actually get rid of everything inside the extension of the predicate A. Right, so I make this empty. So there's no longer anything standing in this A relation to anything else. What that's going to do is that's going to make all of these cases now false. Which means that it's not the case that there is something for x and there is something for y such that AXY. There's nothing we can put in for x or y that's going to make that statement true for the relationship A, whatever that relationship is, that two-place predicate. Which is going to make the left-hand side of this conditional false. When the left-hand side of the conditional is false, when the antecedent is false, then the conditional is true. So this is still going to make the conditional true, even though the thing on the right is false as well. The thing on the right is false because I made all of these false. And it only took one of these to be false to make that thing on the right false, so it's still false when I make them all false. The point is that the conditional now gets to be true even though the antecedent, the thing on the left, is false. So keep an eye out for that. Make sure that you understand that when the antecedent of a conditional is false, the conditional itself gets to be true, regardless of what's happening. It doesn't matter whether you're in monadic predicate logic, propositional logic, general predicate logic. If you've got a false antecedent, if the thing on the left is missing, right, the first thing is not there, if you never have the first thing, then the conditional just gets to be automatically true. Now you might think that's counterintuitive, you might think that's horrible, and that is one of the weird things about the conditional that we pointed out as we went through. But if you accept that, then you've got this easy method, I think, for testing some of these conditionals, namely try to see if the antecedent is false, because if the antecedent is false, then you get sort of the conditional coming out being true for free. Okay. So that gives us a sense of how to do this kind of complex quantified proposition. But now we're going to do a slightly different kind of complex proposition. And this time what we're doing is we're taking the main operation to be a universal quantifier. And we've got now the conditional statement inside the scope of that universal. So let's have a look at what this looks like. So here what we're looking at is something like the following. For all x, if AX, then there is some y such that AXY. So notice that we've got this two-place relation where the x here is bound to this universal quantifier right up the front, and this x inside this one-place predicate A is also bound to the universal quantifier. This y here is bound to the existential quantifier. So basically what we're saying is that for all things, if they're inside the extension of this A here, this one place predicate A, so if they have that property A, then there is something that they stand in this A relation to. So if we suppose that the property of A is the property of being alive, that's the one place predicate, and the two place predicate, and the two place predicate is that X is angry at Y, then what we're saying here is that for all things, if they're alive, then there exists something that they're angry at. Okay? And now if we want to build a model under which this is true, we can do that fairly straightforwardly. So let's just suppose that we've got a couple of objects. I'm not going to do it in terms of numbers, but I'll build a number model for this as well in a moment. But in the first instance, I'm just going to suppose we've got two objects. The two objects we have are snake . That's our first object is snake, and our second object is dog. That fat dog. Let's give it eyes. Big smile. Okay, so we've got snake and we've got dog. And now what we're going to do is we're going to put these two guys into a relationship with each other that is going to make this sentence true. So the first thing to note is that both snake and dog are alive. So snake is alive and dog is alive. So if I have the predicate, the extension of the predicate is alive, which is the A predicate, then I'm going to have snake in here, and I'm going to have dog. Right. So that means that everything here, everything in this little model that I'm building with snake and dog is alive. So the antecedent of this conditional is going to be true. It's going to be satisfied. And now I want to say is that for everything that's alive, there's something that that thing is angry at. So let's suppose that dog is angry at snake, and that snake is angry at dog. So if I were to draw the set of ordered pairs for that, I'd have a set here for A, X, Y. What I'd have is an ordered pair of the dog and the snake, which is how I write that dog is angry at snake, and I'd have an ordered pair of snake and then dog, which is how I write that snake is angry at dog. So given this way of setting the extension for the predicate is alive, this way of setting the extension for the angry at relation, then I've made this statement true. I've said for everything that's alive, everything inside this set of alive things, we've got two things in there, snake and dog, there exists something such that the alive thing is angry at that thing. So if we look here, there is something that each alive thing is angry at. Dog is angry at snake, and dog is alive, and snake is angry at dog, and snake is alive, so we've made this sentence true. Okay, so there's a sort of simple model involving snake and dog that makes this sentence true. If we want to make this sentence false, one way to do it would be to put a little bit of peace into the situation. So if we make it the case that dog is no longer angry at snake, and in fact dog is angry at nothing, dog's just blissing out on being alive and being a dog, then this statement up here is going to, the universal statement is going to be false, because this says for all things, if they're alive, then there's something they're angry at. Dog is alive and dog is not angry at anything. So you've got the first thing, it's alive, but it's not angry at anything. So you don't have the second thing. And so it's not the case for all things that there is something that if they're alive, then they're angry at something. Another way, an interesting way to make this sentence true that we can play around with is to take snake and dog both out of the set of things that are alive. So if snake is dead, if it's a zombie snake, so dead snake and dead dog, and these are the only two things that there are, dead dog, dead, oh hang on, I meant to write dead, not dog. If these are the only two things that there are, and they're both dead, if everything's dead, then the antecedent of this conditional is going to be false for every value of x, which is going to make this universally quantified statement right out the front true for every value of x, because the conditional statement's going to be true for every value of x, because the left-hand side, the first thing, is missing, it's missing an action, it's failing to be there, which, as we've already seen, makes the conditional automatically true. So if we empty out the set of alive things, if there's nothing that's alive in this case, then we're going to make this conditional statement true. The other way, of course, to make it true is to make sure that for everything that is alive, there's something that it's angry at. If we want to make it false, we say that there's something that's alive that is not angry at anything. All right, now that's done with snake and dog, but we can easily just redo this all with numbers rather than doing it with snake and dog. So if we redo it with numbers, we'd have this. So let's get a domain of 2 objects. So before we had snake and dog, now we've got the numbers 1 and 2. We're going to set the extension of A to have both 1 and 2 in it. That makes it the case that everything, before we were talking about X is alive, now rather than talking about alive and dead, we're just talking about these numbers 1 and 2. Whenever A is, all of the numbers satisfy that predicate, which is like saying that everything is alive in the previous model that we were looking at. And now for the 2-place predicate, if we want to make this statement true, we're going to have it that there is something that each of those numbers stands in the relation to. So just as before we could make snake angry at dog and dog angry at snake, here we can make 1 stand in the relation to 2 and 2 stand in the relation to 1, and that's going to make the statement true. If we want to make the statement false, then we can do it in the same way. We can get rid of one of the ordered pairs, so we can make it that 1 stands in the relation to 2, but 2 doesn't stand in the relation to anything. That's like making snake angry at dog, but dog not angry at anything. We can make the sentence false by getting rid of everything inside A, and that's going to make the antecedent of that conditional true, no matter what value A takes. Now, the big central difference between what we're doing in this case and what we're doing in the previous case when we're looking at the situation when the main connective is a conditional is that we're not so interested here in the conditional, although we certainly are interested in that. Rather, the main thing that we're looking at is this universal quantifier right out the front, and we want to see how this conditional behaves with respect to this universal quantifier, and that's key. In the previous case, it was the conditional that was the master of everything, and the universal was in the service to the conditional. Here, it's the universal that's the master of everything, and it's the conditional that's in the service of the universal, and so it's the universal that we're really trying to work out with respect to that conditional, whereas before it was the conditional we were really trying to work out with respect to the universal that was sitting inside its scope. So when you're looking at the difference between these two types of sentences, when you're looking at cases where you've got a complex sentence and the main connective is one of your propositional connectives, it's that propositional connective that is governing everything. Whereas here, when you're looking at a case where one of them, the main operation, the main thing you're interested in is a quantifier, then it's that quantifier that's governing everything. That doesn't mean that there's no relationship between these two things. There's always a relationship between your propositional connective and your quantifier and your propositional connective, but it's the kind of priority of that relationship that changes as you alter whether it's the universal quantifier right out the front or it's the propositional logic symbol that's doing the main work. Okay, so here's a sort of visual representation of that exact type snake-dog situation that I was going through a moment ago. Okay, so let's come back to our model theory and then we're going to look at some more examples. So a model, remember, from monadic predicate logic is a specification of a domain of objects, a specification of the extensions of any predicates, and the assignment of an object to each name where the same object can be named twice, but the same name cannot name 2 objects. Exactly the same thing is true for general predicate logic, so we keep our specification of a model. It's just that, as we've seen, what we do is we use extensions involving ordered pairs or ordered triples. And now we've seen how to build those models and apply them. The last thing we need to do is think about the concept of validity. So remember when we moved from propositional logic into monadic predicate logic, we had to change the concept of validity because we were no longer straightforwardly talking about possibilities anymore, but we were talking about fragments of possibilities, which are models, and we were defining validity over fragments of possibilities, namely over models when we hit monadic predicate logic. So we shifted a little bit how we were understanding validity when we moved into monadic predicate logic. Now that we've moved into a different logic again, into general predicate logic, do we have to change our definition of validity? Well, here's the good news. The definition of validity stays exactly the same from monadic predicate logic into general predicate logic, which is just to say that an argument is valid in general predicate logic when there is no model under which the premises are true and the conclusions false, And an argument is invalid in general predicate logic when there is some model under which the premises are true and the conclusion is false. The only difference between the monadic predicate logic and general predicate logic cases is the structure of the models. In general predicate logic, the kinds of models that you're looking at, that validity is defined over, in each case feature a definition of any n-place predicate that features. So if you've got a two-place predicate, then your models have to have extensions for the two-place predicate. If your sentences or your argument has a three-place predicate, then those models have to have extensions for those three-place predicates, and so on. So the structure of the models has changed, but that structure has just changed because we've shifted from the monadic predicate models to the general predicate models, but the actual definition of validity stays the same. So the validity is sort of still defined over models, but the space of the models, the structure of the actual models, has changed slightly. All right, so the easiest way to get comfortable with general predicate models is to just look at a few. So what I'm going to do is I'm going to look at this model, this particular general predicate logic model, and I'm going to evaluate some of these sentences here against it just to show you how this might be done. And in each case, I'm going to go the hard way. So I'm going to look at the sort of all the values for x, all the values for y, all the values for z in order to evaluate the sentence adequately. Then after that, we'll get to identity. So I'll look at a couple of these to give a feel for how it works. So let's put the model up. Put the model up in this corner. We've got 1 and 2 as our objects. We've got a one-place predicate, which has, sorry, I just have to get rid of that last object. One-place predicate that's just got two things in it. There's a mistake on the slides. I think I put 3 objects inside the two-place predicate, but we just need these 2 objects inside this two-place predicate. We can't have anything inside the extension of a predicate that doesn't appear inside the domain. And then the last thing we do is we set the extension for the two-place predicate. Sorry, the second last thing we do. Then after that, we've got to, oops. Sorry, let me just try that again. All right, the last thing we do is we set objects to names. All right, so there's the model, and now I'm going to evaluate some sentences against it. I'll put the sentence up here and I'll evaluate it down here. So the first sentence I'm going to evaluate is for all x, for all y, if g x y, sorry, for all x, y, g x, y, for all x, for all y, g x, y, just in case there's some z such that p z. Okay, so we've got 3 variables in here, which means that we're going to have to look at every value for x, every value for y, and every value for z. And each time we look at these values, we're getting this splitting feature. So ultimately, we're going to have to look at 6 different instances of this biconditional statement. So I'll put all of the instances up, and then we'll evaluate them. So we start with our x's, x equals 1, x equals 2, and that's going to split to y equals 1, y equals 2, y equals 1, y equals 2, and then those are going to split to z equals 1, z equals 2, z equals 1, z equals 2, sorry, not 6, I'm going to have 8. So 8 combinations that we're going to have to chew through in order to evaluate this sentence. So here's all the values for x, y, and z. And now what I do is I just take this sentence, strip away the quantifiers, and just put in those values into the extensions or the slots following the relevant predicates. So for this first one, I'm going to have g and then the ordered pair 1, 1, because x equals 1 and y equals 1. And then biconditional, and then p 1 in the extension of that predicate. And then I'm going to do that for each of these. So the next one is going to be G1, 1, biconditional P2. Oops. And then the third one is G1, 2, biconditional P1. Then the fourth one is G2, 1, 2, biconditional P2, and then number 5 is G2, 1, biconditional P1, and then G2, 1, biconditional P2, G2, 2, biconditional P1, G2, 2, biconditional P2. Okay, so there's all the 8 combinations, all of the 8 conditionals. And now because I've got this double universal out here, it means that for every value of x and for every value of y, there's some value for z. So it means I need it to be true for all of the values of x, I need it to be true for all the values of y, but I only need it to be true for some value of z with respect to each. So that means that for each value of y, there has to be some z that makes this true. And then for all of the values of x, this has to hold for all of the values of y. So let's just compute these various biconditionals. And once we've computed these, all 8 of these biconditionals, we worked out whether they're true or false, then we can make a judgment globally about whether the sentence up the top here is true or false. Okay, first sentence. In order to work out whether this biconditional is true, we've just got to see whether the ordered pair 1, 1 is inside the extension of G and whether 1 is inside the extension of P. Now one thing we know is that P has everything in it inside the domain. So we know that no matter what we put in over here for P, that this is always going to be true. So let's just put all of our trues in for the right-hand side of the biconditional in every 8 of these cases. So they're all true. Right, so the right-hand side of our biconditionals are true. That means the left-hand side needs to be true in order for the biconditional to be true, and that's just based on the standard truth table semantics for the biconditional. Okay, so let's go back to our 1, 1 inside the extension of G. Is 1, 1 inside the extension of G? Yes, so we know that that's true. Is 1, 1 inside the extension of G? Yes, so we know that that's true. Is 1, 2 inside the extension of G? Yes, so we know that that's true. Is 1, 2 inside the extension of G? So yes, we know that that's true. Is 2, 1 inside the extension of G? Yes, so we know that both of these are true. And is 2, 2 inside the extension of G? No, so we know that both of these last 2 options, these last 2 combinations, the left-hand side of the biconditional is false in both of those cases. All right, so now we've got a value for the left-hand side of the biconditional in each case, and we've got a value for the right-hand side of the biconditional in each case. We can compute the biconditionals. So we know that this first biconditional is true, this second biconditional is true, the third is true, the fourth is true, the fifth is true, the sixth is true, and then the 7th is false, and the 8th is false. Okay, so we've got 6 of these 8 possible combinations where the biconditional is true, and then 2 where the biconditional is false. Remember, these possible combinations of possible values for x or y that we could put in, or x, y, and z in this case, from objects inside the domain. And so what we're going to do now is we're going to try and work out whether this sentence is true or false based on this result for these 8 biconditionals. So what do we need to be the case? Well, we need it to be the case that for every value for x and for every value for y, there is some value for z such that pz. So we need it to be the case that it checks out for every value of x, and it checks out for every value of y, and it checks out for some value of z for every value of y and for every value of x. So when x equals 1 and y equals 1, there's some value for z that we can put in that's going to make the biconditional true, because when z equals 1 or z equals 2, then the biconditional is true. So we know that it's true here and here, so we know that that is true for every value of y. And now we know it's true for every value of z, so we know that it's true for some value of z. Now we look at the second case. Well, when x equals 1 and y equals 2, is there some value for z that we can put in that makes the biconditional true? And again, it's true in both cases. And so we know that it's true there as well. And so we know that when x equals 1, it is the case that for every value of y, there's some value of z that makes the biconditional true. So we've got that first value for x checked out. Second value for x, when x equals 2 and y equals 1, is there some value for z that we can put in that makes the biconditional true? Yes, no matter what we put in for z, that biconditional is true, so we know that it's true when y equals 1. When x equals 2 and y equals to, is there some value for z that we can put in that makes the biconditional true? Well, it turns out that there's no value for z that we can put in because the biconditional is false in both of those cases, which means that it's not true for this value of y, which means that it's not the case for this value of x that every value of y checks out. So we need it to be the case that it's true for all the values of y, but there's some value for y where this whole sentence, this whole biconditional statement doesn't check out. And because it's not true for every value of x, right, so we need it to be the case that for every value of x and for every value of y and for some value of z, it checks out. It doesn't check out for every value of x because we've got a value for x where it's false, and because we've got a value for x where it's false, but we need it to be the case that it's true for every value of x, then this entire biconditional statement is false given this model. Okay? All right, let's take a look at another one and then we'll move on to identity. So we're going to use the same model, but we're going to look at a different sentence. So this model is just that same one. Okay, so we've got the same model, but now this time the sentence we're going to check out is this. For all x, for all y, g, x, y, arrow, g, y, x, arrow, g, x, x. Okay. So that's the sentence. Now, as before, we're going to start by splitting for our variables. We've only got two variables, so we only need to split once for each. But we've got to check we've got to split once. We've got to split twice for each value of x, and then x is going to split for each value of y. And because we've got a double universal out here, we know that whatever we're testing, it's going to have to be true for every value of x and for every value of y. So let's put down our values for x. We've got x equals 1, x equals 2. Those are the two possible values for x. And then for each of those values for x, there's a possible value for y. And what we're going to do is we're going to take that information and we're going to run it through this sentence. So we've got g, and when we've got gxy, so g1, 1, because x equals 1 and y equals 1. Arrow gyx, so g1, 1 again, because y equals 1 and x equals 1. And then arrow gxx, which means that we've got 1, 1, because x equals 1, and it's x with itself. Same thing for the next one. We've got g1, 1, 2, sorry, because it's x equals 1 and y equals 2. And then we've got arrow g2, 1, because the x and the y are reversed here. And then lastly, we've got g1, 1. Next, we've got g2, 1. g2, 1, arrow, g1, 2, arrow, g2, 2. And then finally, g2, 2, arrow, g2, 2, arrow, g2, 2. Okay. So we've got 4 different conditionals that we have to check. Each conditional, all we've done is we've taken the values for x and y and we've plugged them into the ordered pair following the predicates that we're interested in and got rid of the variables. And now we go through to see if those ordered pairs are inside the extensions of the relevant predicates in order to work out whether or not the sentence is true. And ultimately what we're going to be using is the truth table semantics for the conditional. We've got a double conditional, so we're going to be using that semantics twice. All right, let's start with the antecedent of each of these conditionals. I'm just going to go do the antecedent of the first conditional first all the way through. So it's 1, 1 inside the extension of g. Yes, so that's true. Is 1, 2 inside the extension of G? Yes, so that's true. Is 2, 1 inside the extension of G? Yes, so that's true. Is 2, 2 inside the extension of G? No, so that's false. What's nice about that false result for that bottom one is that we know that this conditional here is automatically true because it's got a false antecedent, and so we don't need to check the rest. So we've already got a value for, we already know that when x equals 2 and y equals 2, the double conditional statement is true, so we don't need to check that last case. We've now just got to check the other 3 cases. Okay, we're going to do the first antecedent of this second conditional now. Is 1, 1 inside the extension of G? Yes, so that's true. Is 2, 1 inside the extension of G? Yes, so that's true. Is 1, 2 inside the extension of G? Yes, so that's true. Is 2, 2 inside the extension of G? Well, we don't check that bottom one anymore because we're done with that, so we can leave that one to the side. Okay, so we've got a true antecedent for each of these second conditionals, which means we've got to check the consequent. Is 1, 1 inside the extension of G? Yes. Is 1, 1 inside the extension of G? Yes. Is 2, 2 inside the extension of G? No. So we've got a false there. All right, now we've got to work back and compute the conditionals. We've got 2 trues on the side of this on the second conditional in this first sentence, so we know that that conditional is true. We've got 2 trues for the second sentence for the second conditional, so we know that that conditional is true. And we've got a true false for this third sentence for this second conditional, which is going to make that conditional false. Now to the first conditional, we've got a true true, which makes that first conditional true, true true, which makes that first conditional true, and then true false, which makes that first conditional false in this case. Okay, so these are our final values here for these 4 conditionals that we're interested in, and those are going to tell you what's going on. So what we can do is we can feed this false back to here, this true and this true. We know that when x equals 1, it's true for every value of y, so we know that this, when x equals 1, this doubly quantified sentence is true. When x equals 2, we know that it's true for one value of y, but false for the other. So it's not true for every value of x that every value of y. It's not true for every value of x, such that for every value of y, if gxy, then if gyx, then gxx. And because it's not true for every value of x, for every value of y, then, and because it's the universal out the front, we know that this statement is in fact false on this model. If we wanted to make this statement somehow true on this model, what we'd have to do is we'd have to deal with this third line here. And one way to do that would be to put the ordered pair 2, 2 inside the extension of G. Because if 2, 2 is inside the extension of G, then we're going to get rid of these false values that appeared along this third line. That would all be true, and then it would be true for all values of x and for all values of y, that if gxy, then gy, then if gyx, then gxx. But because we didn't have that ordered pair 2, 2 inside the extension of G, this doubly quantified sentence turned out to be false for some value of x. It needs to be true for every value of x, and so that makes the overall statement in fact false. Okay, now we're going to finish off our understanding of the GPL semantics by looking back at identity. Now remember that identity is a two-place relation, and so in the semantics for general predicate logic, we already know how to deal with the extension of the identity predicate. So remember, identity is just this thing, and it links terms. So it can be, you can have variables, so you can have things like for all x, for all y, x equals y, but you can also have identity linking names like that, or you can have a mix of names and variables like that, and so on, right? So we've got this object which has 2 slots, and into those 2 slots we can put terms and we can put variables. So it's behaving like a two-place predicate inside the language, but we've given it a special symbol. All right, the semantics for general predicate logic, in a very basic sense, carries over to the identity predicate as well. So the identity predicate is a two-place predicate. It's always got something on the left and something on the right. And so its extension is a set of ordered pairs, just like any other two-place predicate inside the language. The difference, however, is that identity inside general predicate logic has the same extension no matter which model you're looking at. So one of the interesting and useful things about general predicate logic is that the extension for a predicate can vary from model for model. So here's 2 models. Okay, and now I suppose I've got the one predicate, A, X, Y. And what can happen is that on one model, this predicate might have, the ordered pair 1, 2 in it, And in another model, the predicate might have a different set of ordered pairs in its extension. And we want this to be the case, remember? So to get a feel for why we want this to be the case, when we've got something like the taller than relation, and we're thinking about models as fragments of possibilities, there are lots of possible ways in which people that you know could be taller than each other that differ from how things are actually. So for instance, suppose you've got two friends, Jeff and Sarah, and in the actual world, Sarah is taller than Jeff. There could be some world in which Jeff is taller than Sarah. And so you want that taller than relation to be able to take different extensions in different possible worlds or different situations. And we reflect that using the model theory by allowing the extension of these multiple place predicates to vary from model to model. Identity has the same extension on every model, so it doesn't have this kind of variance. And that's why we keep it separate from the other predicates. The interpretation, or the way that you understand a predicate like is taller than or something like that, is going to vary from model to model, from possibility to possibility. But identity is always the same everywhere, no matter which possibility you're looking at. So what is the extension for the identity predicate? Well, the extension for the identity predicate in every model corresponds to the set of ordered pairs where for each thing in your domain there is some ordered pair that has that thing in that ordered pair, and every such ordered pair has the same thing in the first slot that it has in the second slot. So what does that mean? Well, it's often easier to just see this rather than to sort of hear the definition. In this model, the identity predicate, in the first model, the identity predicate is going to have an ordered pair for each of the objects. So it's going to have an ordered pair for 1, and it's going to have an ordered pair for 2. And for each of those objects, it stands in the first and second terms inside the ordered pair, inside the ordered pairs that you have. So you can have 2 ordered pairs, 1 for 1, 1 for 2, and the first ordered pair is going to be 1, 1, and the second ordered pair is going to be 2, 2. And what this is supposed to reflect is the idea that objects are identical to themselves, but two different objects are never identical to each other. So you never have 1 being identical to 2 or 2 being identical to 1, because that would be very strange and incoherent. It would be like saying Sarah is the same person, is strictly identical to John, that they're the exact same person. You've got 2 things that are in fact 1 thing. And I don't mean by that Sarah and John pick out the same object. I mean there are 2 objects and they're the same object. That sounds like a contradiction. It sounds like something that's incoherent. And so the identity predicate is respecting that basic thought behind identity, namely that identity is always well behaved, that every object is identical to itself and to nothing else. So over here, the extension of the identity predicate in some sense is different because there are different objects, but the structure of that predicate, the structure of the extension is going to be the same. For every object, there's an ordered pair for that object, and the ordered pair is going to be that object and itself as the first and second term. So here it's 1, 1, 2, 2, 3, 3. If I have 4 objects, then the extension of identity is going to have 4 ordered pairs in it, and the 4 ordered pairs would be 1, 1, 2, 2, 3, 3, 4, 4. If I have 5 ordered pairs, then it's going to be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. It's going to be for n objects, you'll have n ordered pairs inside the extension of your identity predicate, and the structure of those ordered pairs is always going to be the same. It's always going to be an object and itself as the first and second terms. So the identity predicate means the same thing always. It's always that set of ordered pairs where the first thing is in the first and the second slot, and every object has its own ordered pair inside the identity predicate. So in some sense, the identity predicate is sort of shifting its extension, but it's shifting its extension only because the domain is changing from model to model. The actual definition of the extension, namely that you take each object and you put it into some ordered pair, and then it's the first and second terms in that ordered pair, is going to be the same across models. So it's held fixed insofar as you're always structurally putting the same types of things inside the extension of the identity predicate. Okay, so that gives us our definition of identity, and here's just an example with lots of objects in it. We've got 8 different objects. We've got an A predicate, which is just a one-place predicate or a monadic property. We've got a 2-place predicate, the PXY, which has got a set of ordered pairs. And then identity on this model is going to have this set of ordered pairs: 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8. It's going to have that set of ordered pairs in it. If I added another object, I'd have to add another ordered pair, but it would be that same, it would look the same in the sense that it would still be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, and then 9, 9 as well. And so on for every single model. Now, because identity has the same interpretation on every model, we don't bother specifying it in our model construction. We just take it as read that identity is there in every model and it's behaving in exactly the same way in every model. And so we don't bother sort of offering an independent specification in our models when we're building our models for identity. So you can always assume that identity is kicking around inside general predicate logic models, that is. We didn't even have identity inside monadic predicate logic models, so you can't even assume that identity is working in those models. But we can assume that it's working in the general predicate logic models and that it's got the same specification across every one of those models, at least sort of structurally the same specification. Okay, identity has 3 important properties which we hold fixed across every single model in virtue of the fact that we're keeping its interpretation the same. And these three properties are reflexivity, transitivity, and symmetry. Now these 3 properties, I'll explain them to you in a moment, are properties that relations can have. So lots of other relations can have these properties, and when a relation has all of these properties, it behaves in a certain way that is important for various other purposes. So some relations that have these 3 properties are very important in mathematics. Identity is a very important relation inside logic that has these 3 properties. But lots of relations can have these properties, and you can have one of these properties without having the other 2. You could have any 2 of the 3, or you could have all 3, or you could have none. So relations sort of vary with respect to how they stand on these particular properties. Okay, so here are the notions of reflexivity. Reflexivity, when a relation is reflexive, that relation wraps back on itself, which is to say that if something stands in the relation, then it also stands in that relation to itself. So for instance, the relation of being the same person as is reflexive in this sense because you are the same person as yourself, and so that relation is wrapping back on you. Similarly, identity is reflexive. Every object stands in the identity relation to itself. Everything is self-identical. Second property of this relation is transitivity. And transitivity you can think of as a kind of chaining relation. If x is identical to y and y is identical to z, then x is identical to z. So it's useful to just see visually how these things look. So here's reflexivity. If I've got an object, this is reflexive. If I've got an object, and a relation R, then that relation R is reflexive when it's wrapping back on itself like this. When I've got transitive relations, then what I'll have like something like this. When the relation is transitive, if the first thing stands in the relation to the second thing and the second thing stands in the relation to the third thing, then the first thing stands in the relation to the third thing. So that's this sort of way of chaining the relation across a middle object. There are other relations that are transitive. Causation is sometimes thought as a transitive relation. But identity is also supposed to be transitive. But it's sort of transitive in almost a trivial sense. Because everything stands in the identity relation to itself, if you were to take 1 and 1 and 1 and use those as the 3 objects that stand in this sort of transitivity relationship, then the transitivity would check out. So you get transitivity, but you kind of get it for free. It's not a very interesting property of identity. That said, if you were to lose the transitivity of identity, horrible things would probably happen to the kind of logical structure that you're working with. So it's important to have in there, but identity sort of gets it for free. And the last thing that we want is symmetry. So the last kind of property is symmetry, and identity also gets this one for free. And the idea is that when you've got a symmetrical relationship, the relation, if it goes in one way, comes back the other way. So for instance, being a sibling of is a symmetrical relation. If you are your brother's sibling or your sister's sibling, then they are your sibling as well. So that relation goes one way and then it comes back, and that's a symmetrical relationship. And identity is supposed to be a symmetrical relationship. If 1 is identical to 1, then 1 is also identical to 1. So it's sort of comes back on itself, but again in a kind of trivial and uninteresting way, because the relation is never going between two distinct objects, but it is sort of standing in that relation always to itself. So you get these properties like reflexivity, symmetry, and transitivity falling out of the identity relation because of the structure of that relation, because of the way that relation is specified, but not really in a kind of interesting way. Still, those properties turn out to be really important properties of transitivity. Really important properties of identity, and they're things that we need in order to do various things with identity in more advanced logics. It's worth just sort of noting these sorts of properties of relations generally. So the reason I'm drawing these out is because once you see that these properties hold for identity, you can start to look for them in other places and with respect to other relations. So here is a way of specifying the sort of reflexivity, transitivity, and symmetry conditions for identity. But just as I've stated them like this for identity, you can actually state them for any relation. So you could state reflexivity, transitivity, or symmetry for any relation. Now, although we take it as read that identity has these properties on every model because the interpretation of identity is held fixed, if we want to state that any other relation is symmetrical or transitive or reflexive, we have to do that independently. We have to add something else into our system, into our statements of sentences or our argument or whatever it is, in order to get that constraint onto the model. So you don't get these constraints for free with any other relation except for identity. You have to add them in by hand for other relations. Okay, so because we've sort of come to the end of general predicate logic with identity now, at least semantically speaking, next thing we're going to do is look at the proof theory. And we can just sort of reflect on the power of the logic that we've got. And remember at the end of this sort of section on syntax, I showed you how you could translate numerical statements, things like at most, at least, exactly, and so on. Now that we've got a semantics, we can sort of see how those sorts of statements might be constraining the models that they work under. So suppose that I say something like, there are exactly 3 cats. Suppose I say something like that. Remember I showed you how you could translate this sort of sentence out. You'd be translating it out as for all x, for all y, we want exactly 3. I'd be saying there is some x and there is some y and there is some z and x and they're all cats, we want that. So cx and cy and cz, and x does not equal y, and x does not equal z, and y does not equal z. That gets us there are at least 3 cats, 3 distinct cats, and then if we want to say that there's exactly 3 cats, then we say, and for all z, if it's a cat, then either it's identical to x, or or it's identical to y, or so it's going to have to be w. Need a new variable. Okay. Last thing we say is that for all w, if it's a cat, then either it's identical to x, or it's identical to y, or w is identical to z. All right, so I've omitted some of the parentheses here just so I can fit it on the screen. You're going to have to add parentheses for each of these conjunctions and disjunctions and so on. But the important thing to note is just that we can say this sort of thing inside general predicate logic. But now I want to think about what this means semantically. Well, what this means semantically is that a model that makes this true is going to have a couple of interesting features. One interesting feature is that it's going to have at least 3 objects in it. Why? Because there are exactly 3 cats, which means that there are at least 3 cats, and there can only be at least 3 cats if there are at least 3 objects. So your domain, any domain that satisfies this kind of statement, any model that satisfies this kind of statement is going to have at least 3 objects in it. And indeed, it doesn't even have anything to do with cats. If I just look at this logical statement in abstraction from the concept of cats, and I just look at these as symbols, and I try to build a model for this kind of sentence, that sentence is going to have at least 3 objects in it. Otherwise, I won't be able to get these distinctness claims to come out, and I won't be able to get it to be the case that there's at least 3 distinct objects. It's also going to have to be the case that the extension for C is going to have exactly 3 objects in it. In the case where we interpret C as being cats, we're saying that there's exactly 3 cats. But again, if I abstract away from this particular sentence and just look at this logical sentence in isolation, then I get to be able to see that any model that satisfies this sentence is going to have a domain in which, an extension for C in which there are at least 3 objects inside it. So, what's important here is that you get this kind of relationship between numerical quantification and models. So your numerical quantifiers, which is any sentence of this kind, there are at least, or there are exactly, or there are at most, and the kind of structures that correspond to that, the numerical quantifiers constrain your models. Which is to say that in order to make a statement with numerical quantifiers in it, your models may have to be certain size, or have a certain number of objects in them, or have at least a certain number of objects, or at most a certain number of objects. In other words, when you put these constraints on, where you sort of write a sentence in general predicate logic that has these numerical properties to it, like exactly 3 or at most 3, and then you build a model that interprets that, the model inherits the kind of constraints that the sentence is laying down. So it may force the model to have a certain number of objects in it. It may force a model to be finite in that it may not be able to have more than a finite number. It may force a model to be infinite. You've got to think about the ways in which these sorts of sentences actually impose these constraints onto the models that they operate on. And there's the sort of other moving part here is that notion of a reflexive or transitive or a symmetrical relation. It's really numerical quantifiers plus identity that are doing the work here. It's when you start to say things using the identity relation that you put these severe constraints on models. And it's because of the properties of identity that you get those kinds of constraints arising. Which is to say then that there are other ways to put these constraints on models and using other kinds of relations. So another way that you get this sort of thing is if you look at number theory or you look at basic arithmetic and you look at the successor function. 2 comes after 1, 3 comes after 2, 4 comes after 3, and so on. And then you look at the formal properties of that successor function. Is it transitive? Is it reflexive? Is it symmetrical? It's at least transitive, right? And then you look at the constraints that puts on the models, you may find that the constraints that the model are under, like a model that you use to interpret arithmetic, has some interesting properties, and you can actually learn things about arithmetic by exploring the models that underlie it. You might actually also find that there are so-called perverse models, cases where you have an infinite language like the set of natural numbers, where you talk about an infinite number of things, but your model itself is only finite. It's only got a sort of finite structure. It's just that the structure of the model has a kind of looping system in it, in the objects, that enables you to sort of generate all of these objects in the logical language, but that aren't actually reflected in the model. So the general point here, and I think it's a really interesting point, and it only arises once you get to this point with general predicate logic, is that you can put these really interesting numerical constraints on your models based on the sorts of things that you say inside general predicate logic. Which means that some sentences in general predicate logic require models to be of a certain size, and working out which sentences require which models to be of what size is an interesting project that can provide deep insights into things like mathematics. All right, the last part of the course that we're going to move into now, we've just got 2 lectures left, focus on the proof theory for general predicate logic. So what we're going to do is we're going to take our proof theory from monadic predicate logic, our tree system, and we're going to generalize it over to general predicate logic, and then we're going to show you how to prove the validity or invalidity of an argument inside general predicate logic, culminating in the extraction of models from our general predicate logic sentences and arguments. Okay, until next time, thank you very much.